Okay, 10 o'clock. Welcome in online world and real life world, I guess. Welcome back to your favorite class. Yes. Today we're going to start new material on fatigue life. I finished up sort of the thick wall pressure vessel material last week, and I did a practice pressure vessel problem over the weekend and uploaded that to YouTube. So if you want to take a look at a thick wall pressure vessel practice problem, you can go ahead and check that link that I sent out this weekend and go ahead and take a look at that. I did send out another email this morning with a kind of like summary of all of the stuff that we have left to do in the class. So if you got like homework number 7 due this week, you've got your non-circular torsion lab due this week, and then you've got your exam number 2 in the lab section next week. Okay, so there's a lot of information in that email. I plan to send out like practice review problems, much like we did last time, so you have those available to you, and I plan to run a review session again early next week for those people that want to attend that. Okay, so kind of trying to map out all the stuff that we have left, and hopefully you took a look at that. All right, so today we start a new topic, and that's fatigue life. Boy, I got to tell you, I'm getting awfully fatigued by all these political ads. I'm gonna be excited when this like election season's over. Not that kind of fatigue, material fatigue. Okay. So new notes are uploaded, and we'll just go ahead and dive right in and get started. All right, so here we go, fatigue life methods. All right. We've had like some discussion about failure before in this class with those like static failure theories. Remember Tresca and von Mises and Mach's stress theory and all that sort of stuff. And those stress theories are generally good, but in reality, most materials that fail are going to fail in fatigue, like especially most metals, most like ductile metals. So we have to have some theories that we can use to sort of predict when we're going to fail by fatigue, at least something to start with. And generally, fatigue is not well understood scientifically. And so, what I mean by that, I mean, when you're trying to think about how forces interact on like an atomic level and fatigue and how that causes the material to wear out in sort of like a physics, molecular, atomic sort of sense, it's really kind of difficult to actually predict how things like that are going to fail because of just such the complexity of how that failure occurs on such a micro scale. So the best models that we actually have for predicting fatigue are actually kind of like, we just did a lot of experiments and this is the numbers that we found. Okay, that's basically like how fatigue works and how the analysis sort of goes. Okay, so that's how we generally approach fatigue problems. Okay, so let's just dive into this and give a general overview on fatigue, and we'll get into it. Okay, so on many materials, stresses and forces are going to be cyclic. Okay, stresses will be cyclic. Okay, and so it may have this like repeated or fluctuating stress, and in this class we'll generally sort of model it as a sinusoid. Okay, so we'll have repeated or fluctuating stress. One of the images I like to show off is like kind of the stresses that you might anticipate if you're actually taking an aircraft ride from like one place to the next. So I like to bring this picture in because I think it gives a good idea of actually kind of like the complicated loading situation that maybe a real material might go through during its production. So maybe do your best to copy this, or this picture is also in the notes. But I kind of like this idea here. Okay, where you've got this aircraft, you've got all these structures inside of the aircraft that are going through some sort of cyclical applied fluctuating stresses. All right. So during taxiing and landing, maybe some components are experiencing some small compressive stresses that are kind of fluctuating up and down as this, aircraft is going through and over the tarmac and maybe hitting some like bumps, or, the shock absorbers are doing some stuff, whatever. And then you take off and you're in flight, and there's some fluctuating stresses from flight as you're kind of, flying through the sky, and not everything's choppy, you're hitting some turbulence, etc. And then you get into a storm. Hopefully it doesn't look this bad. This looks pretty bad. Maybe you're flying through Hurricane Katrina for some reason. This looks a little bit aggressive, but um, that's pretty bad. But you get the general idea is that it could kind of be a pretty aggressive situation. Has anybody ever been in like really bad turbulence before, when you're just like, oh my god, I hope I don't die? Yeah, okay. Or you like, you feel like you're falling for like a matter of seconds, and you're just like, oh my gosh, I'm gonna die. Yeah, that's scary times. Okay. Anyway, so yeah, maybe that happens to you here, and then maybe you chill out and you make it through Hurricane Katrina, and you're back to like your normal flight. Then you're landing and taxiing, and you've got some compression. And then when the thing is sitting in the hangar for a while, maybe it's going through some thermal loading, okay, as it gets hot and cold inside the hangar. Something. Okay, you get the general idea. Is that there's this series of like fluctuating stresses that are sort of happening. Okay? And so what we want to do is we want to create some models that might predict, if we have all this fluctuating stress, how is that like reducing the overall strength of the piece? Or am I going to run into failure with these like really cyclic loads before I might predict it with some of the other theories? So we want models that capture this behavior and allow failure prediction given these conditions. And the reason we want these models is because typically materials that are going to fail in fatigue fail way below like their yield stress. Okay. So this is because materials that fail in fatigue, so fail under fatigue loading, they may fail at stresses that are like way below yield stress. I'll say markedly. I'll use a big word. Markedly. Do I need an accent over the E? I don't think so. At stresses markedly below the yield stress. Or what I'll say is, maybe let's not say below the yield stress. We'll say below stresses predicted with static theories. So those theories might be some of the ones we talked about, like Tresca or von Mises. Some of the ones we talked about earlier in the course. Okay? And when I say markedly below, it could fail like 90% below yield stress. So could fail 10% of the yield stress. It could be that low. All right, so if you got some yield stress for some steel that's like 200 MPa, you could have some loading conditions where your fatigue is so aggressive that you're failing at 20 MPa, which is crazy to think about, right? Like if you're designing a structure and you say, oh, I got a safety factor of 10 against static failure, I'm good. You ain't good, all right? You really got to think about your cyclic loading in your fatigue failure. So the most simplistic model that we're going to start with is just a model that looks at a sinusoidal stress being applied in sort of a cyclic manner. So most simplistic place to start is with a model sinusoidal applied stress. Okay, so that's what we're going to start with. And we'll sort of build on sort of like a simple sinusoidal applied stress as we kind of make our way through these fatigue notes. All right, so let's look at sort of a general model of fatigue with sort of like the most simplistic model. So general sinusoidal model of fatigue. All right, this basically is exactly kind of what I said it was. So we're going to say that there's some cyclic stress that's being applied. It could cycle between tension and compression. It could cycle between some constant level of tension. So maybe it's going from, like, let's say 15 to 5 in tension. It could, be cycling around 0 between 5 and -5. It could be cycling between -10 and -5 and -15, like around -10, right? So you have all these possibilities. So we're gonna generally assume a sinusoidal model. Sinusoid, SOD, around a mean stress. All right, so let's actually draw this guy. All right. So here, let's say this x-axis is time, and the y-axis is the stress that we're applying. And we're going to assume just a general sinusoid, okay? And let's say that we're centered around some mean stress. Okay, so our sinusoid is going to just kind of traverse with this mean value. So that might look something like this. Okay, and this could continue many times. This is just going to be the general model that we sort of have. All right. We could break this up a little bit further and see that it's a repeating sinusoid. If we're going to apply this cyclic stress like over and over and over, you might want to segregate this into like repeating segments. It looks something like that. Okay, so let's put some general definitions then to this. The first we'll talk about is the mean stress. And that is this value here. Sort of the stress about which we're sort of cycling. So we call this sigma m, and I'll give an equation for that in just a second after I define some of the other terms. We have a min and a max stress. I think that's pretty easy to understand. We'll give those sigma min and sigma max. Those are sort of these maximum values which we reach and minimum values which we reach in the sinusoid. So here this is like sigma max, and this is like sigma min, where it's like the top and the bottom of the sinusoid. Pretty easy to understand that. If we have those maximum and minimum values, we can kind of come back to the mean stress and say that the mean stress is just the average of these two values. So it's 1/2 of the max plus the min. All right. Some other things we might want to define is the stress range. And that's just simply the difference between the maximum and minimum. So here is your stress range. We typically call this sigma R. This is not used all that often, but in some cases is useful to sort of give you an indication of how severe your changes are of the stress that you might experience at your piece. So if your stress range is a significant portion of the yield stress, that's probably a big problem. Okay, so here we have what is the max minus the min. Just the difference in the two. And the last one we'll talk about is the amplitude, which is very similar to the stress range, but is just like half of the stress range. And this is just like, you know, the amplitude of your sinusoid. Right. So here we call this sigma A, which is sort of half of the stress range. Or 1/2 of the max minus the min. Sorry, ran out a little bit of space there. Sorry about that. Hopefully you can sort of see that. And the stress amplitude, that's just the amplitude of your sinusoid, obviously. Pretty straightforward. Okay. So the stress amplitude will be something like this distance here. Right. The last thing we might want to define is cycle time. That's going to be here on the x-axis. That's really not technically true. This was one cycle here. And this is one cycle. Here to here. And so the cycle time, we typically denote as capital N sub t. That's the time for one cycle, N sub t. And the last thing we want to define is total number of cycles. We usually just denote this with a capital N. So it's a little bit confusing. The cycle time is N sub t, and the total number of cycles is capital N. Usually how it's given. Whoa. So there you go. We finally got some definitions here. Okay, so let's actually talk about what happens in your like stress versus strain curve. Stress, strain curve. So let's assume a material with following stress versus strain curve. So we'll assume that it's like a yielding metal. Let's just say some sort of steel. All right, specify here what steel. We have a static condition. You'll see something that looks like this. Here's your strain, here's your stress. You guys probably did this in your like material. Did you take like material science classes yet or not? Yeah, kind of. So you, like stress strain is not completely foreign. Okay, so that's good. All right, so the static condition, you're going to have some initial linear condition, right, while you're loading up the steel. Then you'll hit some yield point. So you sort of understand the general idea of yielding, and then this is going to curve over and probably flatten out to something like this. This is a static condition if you just like load it to failure. Usually we denote this as the ultimate stress sigma u, and here this is yield, which we typically give with sigma y. This shouldn't be too foreign for you guys, yes? We know that this linear portion here is the modulus, right? In fatigue, different types of fatigue loading that you might experience. And let's just say that we're fatiguing with a mean stress of 0. What I mean by that is that your sinusoid is basically around 0 stress. Let me maybe draw this a little bit. Give myself a little bit more space here. And since we're going into the negative, maybe we'll give ourselves a little bit of space. All right. So for fatigue loading, what you'll typically see is either high cycle or low cycle fatigue. We have different situations. So when I talk about high cycle fatigue, I only have elastic response. So let's put that here. We can have 2 types of fatigue. That would be high cycle fatigue, commonly given HCF, and this is elastic range only. Okay, so for high cycle fatigue, what you're doing basically is I'm going to load up, but I'm not going to get anywhere near what would be like this yield stress here in either direction. Okay, so I load up, cool, and now I'm coming back and I unload to the same distance here, cool, and I reload back to 0 like that. Okay, I'm constantly kind of like going up and down, back and forth, and only like this elastic range. Okay, so this is high cycle fatigue. It's kind of going through this sinusoid that just sort of looks like this, around this sort of trajectory. Imagine those are supposed to, it's all supposed to be on top of each other. I just can't, it's hard to sort of draw that. That differs from low cycle fatigue. I'll just say for high cycle fatigue, many cycles possible. We're talking for high cycle fatigue, usually greater than 10,000 cycles. All right, that differs from low cycle fatigue. LCF, where we have some plastic portion. All right, some plasticity. So if I want to draw that on my load displacement curve, my stress is going to be so aggressive that I'm going to go beyond what would typically be like the static yield value. So here I'm going to load up, load up, load up. I'm going to get to a point where I would have yielded in static, and I probably am yielding in fatigue here. Turn over slightly, but I haven't quite failed 100% yet. Okay, I've turned over, I've got a little bit of yielding, a little bit of plasticity somehow, but I haven't quite failed it entirely. All right, I haven't gone to the ultimate stress. So now I unload. Let's be a little bit more aggressive here with my line. So I've hit yield. Now I unload and I go back the same more or less amount in compression, and now I start to like level off there in compression. And I come back around, and this sort of pattern develops. All right, this sort of thing over and over and over. Okay, this is low cycle fatigue. And that's some plasticity getting introduced into your sample, all right? Because you're kind of loading it beyond the yield stress, which is yikes town, okay? I brought a demo piece with me today for this particular purpose. Who has seen a pencil that looks like this before? Basically everybody, all right? This little like big pencil. Who has ever taken one of these pencils and taken this tab and like pulled it back and forth like very aggressively to break it off? Literally everybody has done this. Please tell me. Okay, so the idea for high cycle fatigue is that I could take this tab here and I could like do a little bit of stress on it over and over and over and over, and it's really not going to fail anytime soon. I could have tens of thousands of cycles of like this little elastic loading and unloading on this particular tab, and it's probably not going to fail anytime soon. All right, it's because I'm not introducing any plasticity. I'm not going past like the yield stress of this little like hinge on the back side of the pencil. Okay, but as soon as I start getting more aggressive with it, rawr, start pulling it beyond like what would be a yielding condition for the plastic, you'll start to see some like whitening in this hinge area here, and it becomes very easy to break it only after like 5, 10, 15 cycles, right? This is a low cycle fatigue, a low amount of cycles required to fail it because you're introducing this plasticity. Okay, so if I get more aggressive with it, roar! I could eventually break it off if I wasn't super weak. Okay, there you go. Okay, so now I've broken it off just by introducing like a plastic sort of fatigue behavior. Rest in pieces. Okay, so there you go. It's the difference between high cycle fatigue and low cycle fatigue. Here, much less tolerance, so few cycles to failure. And so this is usually less than 1,000. All right, so hopefully you think of that pencil example. Okay, we haven't really talked at all about any models yet. We've only really said that like, yeah, we're going to think about the sinusoidal application of stress and sort of what happens in that condition. And you could think of getting plastic or not getting plastic with high cycle and low cycle fatigue. So let's actually get into what these models look like and what models there might be. Okay, so like I mentioned before, fatigue is not well understood scientifically. Okay, not as well as like some of the other topics we've talked about, like the elastic modulus. Elastic modulus, you can get a pretty good handle on what that is, what's going on physically, and what that actually means. All right, fatigue not really that well understood scientifically, and so most models are analytical. Sorry, most models are empirical models. No, I shouldn't say most. I should say all of them are. Fail you. Empirical. What I mean by empirical is that they're derived from experiment. That's what it means to be an empirical information. All right. The three most common are the following. By far the most common is the stress life method. If you're doing anything in a non-academic setting, like any industrial setting, and you're doing fatigue analysis, almost certainly you are using the stress life method. We'll talk a lot more about this going forward. Another very common method is the strain life method. Okay? This one is much less frequently used, but kind of derived from the same general ideas, except I think more people are comfortable with doing a stress analysis rather than a strain analysis. I think it's just generally true, so people have favored the stress life versus the strain life methods. And the third, here this is the linear elastic fracture mechanics method. Okay. This method requires that you know an initial pre-crack size. So it requires knowledge of an initial flaw. Okay? These two first methods do not. No. Do I want to use this fancy word here? I can do it. A priori. A-P-R-I-O-R-I. Knowledge of flaws required. All right, so what do I mean? The linear elastic fracture mechanics method. If I had some rectangular bar here, and I was pulling this in like cyclic tension, so something like pull, release, pull, release, pull, release, pull, release. The linear elastic fracture mechanics required that I would have some like knowledge of a crack inside the material for this theory to sort of go and function. So if you go to graduate school and you study mechanics, you will look at fracture mechanics theory in much more detail. But fracture mechanics is quite complicated. So for that reason, we're not really going to dive in on the linear elastic fracture mechanics method. I just want to throw it out there so that you know that it exists. And since the stress life method is much more common than the strain life method, we're going to limit the scope of our discussion in this class to be a really deep dive on the stress life method. This is by far the most common that's used in an industrial setting. There are I provided notes on strain life and linear elastic fracture mechanics method. So these are on Blackboard, but I will not test you on these. All right. So if you go to Blackboard, I have some notes there on the strain life method. We're not going to discuss it any more than what I'm talking about right now. Fatigue life curve for strain. Linear elastic fracture mechanics requiring upon a pre-crack. Paris law, which is dealing with that, etc. Okay, so that's all I'm really going to say about available on Blackboard if you'd like to check them out. Otherwise, we're going to just focus on stress life method. And I'm not going to test you on strain life or linear elastic fracture mechanics. Okay. So that's an overview of your methodology and sort of what is to come. So let's talk a little bit more about the stress life method. And what I need to introduce for the stress life method is a concept called the endurance curve. You guys talked about endurance curves yet? Like material science or anything? No endurance curve discussion previously. Yes, Adam has? A little bit? Okay. So we have maybe like a little bit of knowledge on endurance curves. All right. But let's dive in on the stress life method. Maybe once I put it up, you'll kind of recognize it. Specifically the endurance curve. Okay. Like I said, all of the data and all of the predictions that we have for fatigue come from experiment. So all of the things that we do based on fatigue testing, we have to have some baseline experiment that everyone agrees upon. Okay. And the baseline experiment that we're going to do is we're basically going to give varying levels of stress amplitude to a piece with no mean stress, okay? And then see how many cycles it takes for that thing to fail. There's a standard experiment to calculate this, and that experiment is called the RR Moore high-speed test. So let's talk about that. So since method is empirical, we need a standardized test. Okay. What we want is we want a sample 0 mean stress. Okay, so if you're thinking about your sinusoid, that is centered around 0. Okay, this is 0 mean stress. It's your average stress from your sinusoid is 0. And we will vary amplitude and count cycles to failure. Okay, so maybe this is like test number 1. And then you run another test with 0 mean stress, with just a more aggressive amplitude. Okay, and this is test number 2. Where obviously the stress amplitude for test number 1 is less than the stress amplitude for test number 2. Let's say number of cycles to failure given by capital N sub F. Number of cycles to failure, N sub F. So it would be pretty obvious that if we had a higher stress amplitude for, let's say, like test number 2 here, that the number of cycles to failure for stress number 2 should be lower than the number of cycles to failures for stress number 1. So it's pretty obvious to see that the number of cycles to failure for test number 1, since the stress amplitude is lower, we're going to have more cycles to failure for test number 1 than test number 2. I think that is rather intuitive. Yes? Okay. What I want to do is I want to do a lot of tests where I'm varying the stress amplitude just a little bit and seeing if I get maybe 100 cycles to failure less, or how many cycles to failure less. Okay? So the test that is used to do this, counting number of cycles to failure is called the RR Moore high-speed test. Sometimes called the high-speed rotational test, or high-speed, let's just call it rotational fatigue test. Here is the idea. Here's my schematic. I have a axisymmetric specimen. that is more or less round. Okay, something that looks like this, comes out flat. Here's my round sample. And it curves in the middle. It has this radius of curvature to get me to some point where it's like the thinnest it can be, here. And then it comes back out. Here, comes back out. Here. And it's sort of the same on the opposite side. Okay. Terrible line here. Okay, here's the general schematic, what this thing looks like. So here's the specimen. The idea here is that there is an axis that runs through this. And we're going to rotate this thing around. So we're spinning. Some motor giving some rotations. All right, some RPMs on this thing. In its current condition, I don't have any stress on this piece. It's just here and spinning around. I mean, maybe there's some centripetal forces that are acting, but generally very small. So what I want to do is I want to apply some sort of stress to this thing where I'm focusing some stress amplitude in that center region there. All right? The way that I do that is I place this into 4-point bend. So I'll say place specimen in 4-point bend while rotating. Okay? So what that looks like is, yeah, let's do it this way. Maybe I'm loading here, here, here. I'm loading here. Okay. If I do that, my distribution of the moment as a function of the length of this bar, who remembers these from statics? Yeah, very exciting. Looks something like this. Here, this is the length of the bar x, and here this is the moment applied inside of this member. Remember these bending moment diagrams from statics? Are you crying yet? So the moment is more or less constant over this region between these two internal pins of the 4-point bend. Right? So where the sample is the thinnest, or the smallest sort of cross-section here, highest stress. And that's because we know that the stress goes as like my over I. As I is small, stress gets big. Now at this particular point, when I'm looking at this particular specimen, right now, the bending moment is going to create for me a compression on this side. And a tension on this side. Okay? As this thing spins around, the point that is in compression now, after this rotates 180 degrees, will be in tension after 180 degrees of rotation. Okay? So the idea here is that you just put this thing into 4-point bend and you spin up this motor, then this cross section here is going to alternate in compression and tension as you spin this thing around and rotate it. So every 180 degrees, you're going to go from compression to tension, another 80 degrees, tension and compression. So every time that you cycle with the motor, this particular specimen, you're going through like one sinusoid of this stress that we've sort of modeled. Okay? So this gives cyclic tension and compression with similar amplitude and zero mean stress. Okay, so you just load this thing in 4-point bend. You get some motor at like a zillion RPM, and there's some, you know, what's the encoder? Thank you. On the back end of the motor, counting how many spins that you're doing. And then as soon as this thing fails, your encoder stops counting and it tells you how many cycles you have to failure. Pretty slick test. If done well, it actually only takes a matter of like maybe a couple minutes for like a million cycles. It's pretty cool. Okay. All right. So this will give you number of cycles to failure for many stress amplitudes. When plotted sigma A as function of number of cycles to failure, you generate what's known as the endurance curve. And that looks like this. Number of cycles to failure on x-axis, which is a little bit strange considering it's like the dependent variable, but that's generally how it's done. And here's your stress amplitude. This is the independent variable. Here put on the y-axis. I think this is strange, but that's the way that it goes. On the very low end, if we were to fail in 0 cycles, that's basically failing in static condition. So in the case when you fail in a static condition, the number of failures, cycles to failure being 0, this is just going to be your yield stress, sigma y. Sometimes sigma y is used, sometimes the ultimate tensile strength is used. They're both kind of used interchangeably. So let me make this a little bit more clear. Here's your stress amplitude. This could either be the yield stress or the ultimate stress. Both are presented in the real world. So we could consider this as like one data point. How this data typically looks then is as you decrease the stress amplitude away from what would or static ultimate failure, you allow yourself more cycles, more cycles to failure. So, in the pencil example, my stress amplitude when I was very aggressive was very high. So I only had a few cycles to failure. That would look something like this. Okay. So here I'm decreasing sort of the stress amplitude. So how large is my sinusoid? And because of that, I'm getting more cycles to failure. Right? And early on, we're still kind of in a region that might cause plasticity. So let's say that this is just the ultimate stress. And here, this is your yield stress. Let's just go with this model here. This condition, you still have low cycle fatigue. All right, so we have that plasticity occurring, and this is that general region. All right, we're going above the yield stress with our stress amplitude. and it looks something like this. In the high cycle fatigue, where we're not going elastic with our character, we get a little bit different behavior, and this actually like falls a little bit more quickly. A little bit more aggressive on the downfall. I will say that this transition from low to high cycle fatigue is somewhere around the like 1,000 cycles, approximately. This is about where this occurs. There is some stress that we could apply, however, some stress amplitude that is so low that it would never cause failure. All right? Think of like if I very gently touched the top of this table with like barely any force. Okay? I could do this a billion times and the table's never going to fail. Okay? So what I mean by that is there is some stress amplitude where you will never fail in fatigue. And that value, maybe let's say is over here, you would start to see some situation where you go below that amplitude and you will never see failure. Infinite. Right? This idea here we call the endurance limit. That is typically given as capital S sub E. So below endurance limit, which is this S sub E, you will not fail in fatigue. Not all materials have an endurance limit. Okay, that'll be it for today. I'll show some examples of these endurance curves on Wednesday. All right, that's it for today. Thanks for coming.